over the last century, we as astronomers and cosmologists have done a very good job of figuring out what the universe is made of and roughly how much of each component there is. So here's a nice little pie chart. We have dark energy is actually the largest component. I will not talk about it. Dark energy is an even bigger can of worms than dark matter. Stay tuned for future Astro and Tap talks. Dark matter, however, is the predominant matter content. There's roughly 5 times as much dark matter as there is regular matter. We refer to it as baryonic matter, and that includes stars, hydrogen, helium, neutrinos are a type of particle, and heavy elements are us and the Earth and everything that we interact with. So how do we know that dark matter is there? Historically, the first evidence for dark matter came in the 1930s. There's a very cool Pasadena and Caltech connection. Fritz Zwicky was a Swiss astronomer and a professor at Caltech. And he used the Mount Wilson Observatory over on Mount Wilson and the Palomar Observatory to observe nearby galaxies. Or not, actually, they're not that nearby. But he looked at an object called the Coma cluster, which is a cluster of galaxies. The way that planets can orbit a star, galaxies can be bound together by their gravity. But they each have their own velocities. And so he looked at these galaxies and he measured their velocities, and he realized that just based on their velocities, they should all be flying off into space. They shouldn't be bound together the way they were. And so he hypothesized that there was something called dunkle Materie, or dark matter. German was the lingua franca of science at the time, holding it together. This didn't get too much traction at the time. There were a lot of uncertainties about in his calculations. Obviously, the instruments he used weren't nearly as sophisticated as the instruments we have now. So it was about another 40 years before there was more conclusive evidence that really swayed the community, that there was something else in the universe that we couldn't see. So Vera Rubin, pictured here, and yep, Vera Rubin, my scientific idol, measured what we call a rotation curve of galaxies. So imagine you're on a carousel, and it's moving around in a circle, and you're near the edge of it. You have to hold on to keep yourself from flying off of it. This is what happens in a galaxy. The stars and gas in a galaxy orbit the center circularly. That's how you end up with a disk and spiral structure. But the thing that keeps them from flying off into space is gravity. And they measured the rotation, the velocity of the gas in the galaxies, and they found that you can estimate the mass of the galaxy based on the stars that you observe, and they found that there was about 5 times more matter in the galaxy than the mass of the stars would suggest. So that's what they called the missing matter problem, and that was the first evidence that people really took seriously for dark matter. Since then, there's a lot of other evidence. There's cosmological measurements like the cosmic microwave background, which is light that's an echo of the Big Bang. There's the bullet cluster, which is another cluster of galaxies. Actually, it's 2 clusters of galaxies that have merged. And the blue here, do I have a laser pointer? I don't think I do. Yeah, I don't. Oh, okay. Yeah, bullet cluster, top right. Thank you. Yeah. Yeah. Yeah, the blue here is where the dark matter is located. And yeah, the dark matter, the two galaxy clusters collide and the dark matter passes through each other. However, the gas in the galaxy clusters interacts with each other and it lags behind. It's shocked. And we can observe this separation, and that is some of the most conclusive evidence for dark matter that we have. The last piece is there have been recent observations of galaxies that don't seem to have any dark matter, or at least very little. So, yep, that's the one in the bottom. We call this an ultra-diffuse galaxy. Actually, this discovery was announced in my first year of undergrad by Yale researchers while I was there. It was very exciting. At the time, I was like, wait, are the galaxies supposed to have dark matter? Yes, but I did not know that. And so this is essentially an ultra-diffuse galaxy is an old galaxy that's mostly made up of stars, a little bit of gas, and it's kind of fluffy. It's like a cosmic cotton ball is what they call it. And so you can add up the mass of the stars and then figure out the mass of the galaxy otherwise through indirect gravitational measurements. Gravitational lensing is what you would usually use for instance, the bullet cluster. Essentially, a very massive object can bend light around it. And those are basically, it ends up being about the same amount of mass. And so that's how you know that the galaxy doesn't have any dark matter. And that's convincing because imagine that you were in a sandwich shop and it's full of peanut butter and jelly sandwiches. You've never seen a peanut butter and jelly sandwich before in your life. And suddenly you come across a sandwich that's just peanut butter. If you didn't know that there was just the peanut butter, you would think that peanut butter and jelly might just be the same substance. But if there's one that's just the peanut butter, that means it has to be its own thing. So that's how we know that there has to be dark matter, even though this galaxy doesn't have any. Beyond that, what do we know about dark matter? And the answer is some things, but not a whole lot. We know it interacts with gravity. That's the only way we've measured it. It doesn't really seem to interact with much else, and if it does, it doesn't do so very strongly. If there was dark matter hovering in front of me and I reached out and tried to touch it, it would just pass through me. If I tried to shine a flashlight on it, the light would just scatter off. You wouldn't be able to see it. And so that also makes it particularly challenging to detect. I'll talk about that in a few more slides. We also know that it's cold. And we don't mean in terms of necessarily thermal temperature, like it was a really hot day today. This means kinematically cold. So on a microscopic level, a fast-moving particle is hot. This does actually translate to the temperature we feel. And here we say hot versus cold relative to the speed of light. So a cold-moving particle is slow relative to the speed of light. A hot particle, and originally one of the first hypotheses for dark matter was that it had to be a hot particle because we knew about neutrinos, which are a type of particle that don't really interact with very much, but are affected by gravity. But they move at nearly the speed of light. We know that dark matter is not hot, and here's why. So in the early universe, right after the Big Bang, all of the particles in the universe are basically in a giant thermal bath. Very hot, very dense, kind of soupy. And as the universe expands, this bath cools and some of the particles start to leave it. And the structure of the universe that we observe today is affected by how fast the dark matter was when it left the bath. Assuming that it was ever in the bath in the first place, which according to some models, it doesn't have to be. So here's my nice little diagram. The cold dark matter is very slow moving when it leaves the bath. The warm dark matter is moving a little faster, and the hot dark matter is just streaming out. And then this dark matter, if it's moving really fast, it's what we call free streaming. And it moves so fast that it escapes the pull of gravity for a very long time. And that means that it doesn't clump. Here, I'm going to move on to the next slide. Can I get this to play? Oh no, what did I do? Oh, there it goes. Yeah, so this is a simulation of dark matter particles. These are cold dark matter. And you can see it's moving forward in time. It gets clumpier. You start out with like these very small structures and they merge into bigger ones. This is what we call hierarchical structure formation. Small things merge into bigger things. And this kind of web structure is what the universe we observe looks like. If your dark matter is moving too fast, none of the small things form in the first place. They don't collapse. They just fly away and never form what we call dark matter halos. So this is another simulation. On the left, we have cold dark matter. On the right, we have warm dark matter. And the difference is pretty pronounced. All of these little features, these subhalos, the tiny ones in the cold dark matter, are erased in the warm dark matter simulation. And we now know from comparing our observations of the universe to our simulations that hot and warm dark matter erase too much structure. So that's one of the first things that we established about dark matter, is that it has to be cold. And this came roughly in like the 1980s and 1990s. So beyond that, what is dark matter? We have a lot of candidates. This is a very busy Venn diagram of various theories that have been put forth by particle physicists. The one parameter that we can kind of use to make sense of all of this is the mass of the dark matter particle. Assuming that's a particle, we see here on the far right, it doesn't have to be. It could be an astrophysical object like a black hole. And I guess I'll start from the left and explain this. An axion or ultralight dark matter is very small in mass. This whole plot spans 80 orders of magnitude. So that's 10 to the 80. This is huge. As we can see here, I've marked the position, the mass of an electron and a proton, then a human, and then the sun. So these ultralight particles are at least 20 orders of magnitude lighter than an electron. They're tiny. That means that they behave more like a wave than a particle. This is from the quantum particle wave duality. Beyond that, anything that's lighter than that, actually, we can rule out because the wave wouldn't fit inside a galaxy. Then I did lie a little bit about warm dark matter being completely ruled out. There is a tiny little bit of that's still possibly allowed, and that's corresponds to what we would call maybe a light dark matter. We say that it's light relative to a WIMP dark matter particle, which is a weakly interacting massive particle. Great acronym. And WIMPs were actually kind of the quintessential cold dark matter candidate for many decades. And there were good theoretical motivations for it. I don't think I have time to get into them. It's possible that dark matter is capable of forming structure like the structure we see around us. So you could have atomic dark matter. And then, as I mentioned, you could have dark matter particles that are black holes that form in the very early universe. They need to form early as opposed to the astrophysical black holes that, like, you might hear about at most other astronomy on tap talks, because you need them to shape the evolution of the universe over cosmological timescales. However, we know from lensing surveys, so you can look at a star and see if there's a tiny little gravitational lens from some object near it. This is a method that's used to identify exoplanets sometimes. You could also try to use it to identify primordial black holes. We haven't found any, so they're mostly ruled out as 100% of dark matter. It could still exist, but they would just be a tiny fraction of the dark matter. Is dark matter necessarily one type of particle? It doesn't have to be. The standard model of particle physics, which makes up everything we interact with and know about, has many, many different particles, as we can see here. all of these particles have been detected. Most recently, the Higgs boson, which is in yellow on the top left, about 13 years ago. In the standard model, you have particles, and then what we call bosons. These are the red particles, which are force carriers or messengers. They're what communicates forces between particles. So for instance, the electromagnetic force is communicated by photons, which are light particles. You could have something like that that makes up dark matter. Many different dark matter particles that can talk to each other, just like the standard model does. And it's possible that they even communicate with the standard model, but they just do so infrequently that we haven't been able to detect it yet. However, a lot of our prospects for detecting dark matter do assume that there is some very weak interaction with the standard model forces that we can observe. So here, there's three primary methods that researchers use to try to identify dark matter. The first is to say, okay, I really think dark matter is a WIMP. And then you design an experiment that looks for WIMP-like particles. In general, these experiments have to be shielded from things like cosmic rays, which are really energetic particles from the sun and other astrophysical sources. So you put the experiment 2 kilometers underground. This one, the Super CDMS experiment, is in Sudbury, Ontario, in a nickel mine. And I visited. It's very cool. That's also the day I learned I was claustrophobic. And we call that direct detection. And the upside to it is if you detect a dark matter particle, great, you've detected dark matter, you're going to win a Nobel Prize. It's pretty conclusive. The downside is you do have to make assumptions about the type of dark matter that you're looking for, and then build your multi-million-dollar experiment around it, which is costly and time-consuming, and then you run it for a very long time, and to date, we have still not directly detected dark matter. On the other hand, what astrophysicists tend to do more of is indirect detection of dark matter. So you can either look for evidence of dark matter in space. Wow, the parrots are actually loud. Great. And so here I show a map of gamma ray emission from the Milky Way, measured by the Fermi Space Telescope. It's thought that some types of dark matter could have a particle and an antiparticle. And then, just like normal matter, when the particle dark matter and the antiparticle dark matter meet, they annihilate and produce light, a photon. And this requires your dark matter to be pretty concentrated. So the place we would look to see this is in the center of the Milky Way, which is the most dense region of the Milky Way. And there actually is a gamma ray signal that people have discussed being from annihilating dark matter, but this is still very controversial. And there's other more astrophysical explanations that are less exotic. The other way, which I've talked about a fair amount now, and is still to date the only way that we have detected dark matter, is inferring dark matter from its gravitational effects on the galaxies and stars and gas that we can see from telescopes, both on the ground and in space. The great thing about this is it lets us be very creative about how we can use data from a bunch of NASA missions and other ground-based telescopes that may not have necessarily been designed to look for dark matter in the first place. Many dark matter models make predictions for things that would be visible, for instance, in gamma rays, like I just mentioned, or in X-rays. And then I did a search of all of these different NASA missions, and I put a circle around the ones that have been used to constrain dark matter, which is basically everything on this plot except for the exoplanet missions. So it's a very interdisciplinary field of research. That said, as Cameron alluded to, Yep. A lot of these missions are imperiled by the proposed White House budget. This plot also doesn't show the different dark matter direct detection experiments, which are mostly funded by the Department of Energy and NSF, and ground-based radio telescopes, which are really important. The first observations of dark matter from Vera Rubin were radio telescope observations, and that's mostly NSF. So if that budget goes through, our prospects for figuring out the nature of dark matter in the near term are imperiled. But beyond that, to talk a little bit about what I actually do in my day-to-day work, if we are looking at things like galaxies to try to determine the nature of dark matter, we have to be able to separate out the dark matter from everything else that's going on in a galaxy. The stars, the gas, the black holes. Galaxies are highly dynamic, and sometimes the things in a galaxy can have signals that mimic what we might expect from a certain model of dark matter. So this is a simulation that I ran recently. It's a Milky Way mass galaxy. On the left-hand side, I ran the simulation with cold dark matter. On the right-hand side, I allowed the dark matter to talk to each other. There's an additional attractive interaction. Essentially, you're making gravity a little bit stronger on certain scales. And it might be hard to see if you're far away, but there's slightly more substructure in the one on the right when you modify the dark matter. And this is something that's going to be testable in the near future. There's been a couple of recently launched space telescopes that are finding new things, like the James Webb Space Telescope, which has identified really early forming galaxies. But the most exciting new missions are just getting started or launching in the near future. I've shown the first image from the Vera Rubin Observatory, named after Vera Rubin, of course. And they released this a few weeks ago. There are 10 million galaxies in this image. You can't see all of them, obviously, but in terms of it's the largest camera we've ever built. And in terms of being able to find new galaxies in new ways to test dark matter, this is going to be instrumental. So if all of those like extra little dark matter halos that were in my simulation are there, the Rubin the Rubin Observatory will be instrumental in finding them. So will the Roman Space Telescope, which is launching in a few years. Beyond that, just to give a little bit of a summary of the state of the field, there's a lot of direct detection experiments running. For a long time, they mostly focused on finding WIMP dark matter, but more recently, they've been expanding into other different types of dark matter, like axions, lighter dark matter models. There's been no conclusive detection, and the constraints on WIMPs are getting increasingly tight. There is one group that claims that they have a strong signal of dark matter, but this is highly controversial, and a bunch of other groups have not been able to replicate it. My personal take on it is not a detection of WIMP dark matter. Beyond that, still to date, our only evidence of dark matter is from gravitational inference. All right, I'll end here. Thank you for your attention. I'll take questions.